Well, I want to ask you about some other studies you've done recently. So you did some on using LCMS for in vivo neurochemical monitoring. So why are new methods needed for that?
So this is definitely a never-ending story, I would say, with the in vivo neurochemical monitoring. Years ago, people started putting probes in the brain to try to measure neurotransmitters, and either sampling probes, which is what we work with, where you can collect fractions and then analyze them, or very small microelectrodes that can be put into different brain regions to look at specific neurotransmitters. And if you just think about all the things that the brain does, and from controlling sleep to when you want to eat to whether someone's going to take drugs or not, to what happens in different disease states, and the trillions of neurons there are and all the different brain regions there are, you can imagine we don't know a whole lot about what's going on right now. So from an analytical chemistry point of view, the idea of being able to measure the chemicals that are associated with that is exciting, and I think that the better techniques we have, and better means better temporal resolution, better spatial resolution, better coverage of the neurotransmitters that are being released, the more we're going to be able to learn, and the more we're going to be able to sort of solve some of these big questions about the brain.
So what are some of those better methods?
So for us, actually a very simple thing that we did that's turned out to be pretty popular and is helping us a lot is, for many years, if you look at how people were analyzing neurotransmitters, so that is, say, in these dialysis fractions that we would collect, it depended on what neurotransmitter they wanted. If they wanted to do dopamine or norepinephrine or serotonin, they would use liquid chromatography with electrochemical detection. Very sensitive, simple, work good. If they want to do amino acid neurotransmitters, they would derivatize them and make them fluorescent, and then do LC with fluorescence detection or CE with fluorescence detection. And it just seemed crazy to me in this era of omics that we weren't going to just measure all the neurotransmitters at one time. So we set about trying to develop a method to do that. It turned out to be a little harder than I thought. We thought, oh, this will be easy. We'll just use helic chromatography with mass spec. It'll work. Well, the sensitivity wasn't good enough. So the compounds are retained well on helic columns. I should mention most of these neurotransmitters are very polar. They're retained very well, but they're just not very sensitively detected, not sensitive enough, let's put it that way. So we went through a sort of iterative process, thinking about what we want to do, and ultimately hit upon doing this derivatization method where we treat the neurotransmitters with benzoyl chloride. That puts a phenyl group on, eliminates one of the polar groups, makes them pretty hydrophobic, and now they're retained in reverse phase. So we can use a reverse phase column for these guys. We found it enhanced their sensitivity from 10 to 1,000-fold. So all of a sudden, we had a technique that could measure all the small molecule neurotransmitters, shouldn't say all, but almost all the small molecule neurotransmitters, and all their metabolites in one shot. And so that's just been great, because now when a collaborator comes to us and they said, we want to look at acetylcholine in this problem, it's like, okay, we got it. We want to look at dopamine in this problem, we got it. So whatever it is, we have the answer to the questions, basically. We'd be able to look at, and sometimes people don't know what neurotransmitter is important, and then we're covered as well. We can do sort of a neurotransmitter omics type study for them and look at all the transmitters at one time. Yeah, we've had many, many collaborations as a result of that particular development.
And is the derivatization process itself, is that time consuming or very involved?
Yeah, that is one of the great things about benzoyl chloride. It comes in a liquid form, and literally you can just aliquot it in, and by the time you would do that, get it mixed up, it's ready to be injected on the LC. It's a very, very fast reaction. Now we do a few other things. We actually can get internal standards for everything, because we have C13 labeled benzoyl chloride as well. So we would add the label form of all these metabolites in as an internal standard usually. Acetylcholine actually doesn't get labeled, so we just added in an internal standard for it separately. So there's a couple extra steps, but overall, the derivatization is very fast. And I have to say, I was a little bit skeptical about doing derivatization for LCMS, because I usually teach my class that LCMS should be able to measure things. You don't want to do derivatization. If you're going to do that, you might as well do GC. But this just works great, and it's very easy to use. So like I said, we've shown other labs how to do it, and it really doesn't slow you down at all versus just doing a regular LC, I would say.
Fantastic.
Yeah.
You know, we actually had a blog entry not that long ago from Kevin Shug saying that he thinks that derivatization is underutilized.
Yeah.
I mean, do you share that view now, or?
I'm starting to, yeah. I mean, I think that there's a lot to be gained from that. So I think what happens is people look at LCMS and they realize that for certain things it's very sensitive and the reverse phase columns work very well. But then we start kind of looking at specific, and you can see all these metabolites, like, oh, it's working great. But then we start looking for specific metabolites. You go, oh, they're not there. Why aren't they there? Well, we're not seeing them because they're pretty low concentration and they just don't ionize all that well. Derivatization lets you improve ionization efficiency, lets you control the retention. It's really a nice thing to do if you don't have to, obviously you don't want to, but I mean, I think it does solve a lot of problems. And it gives you selectivity too. I mean, you know what, you can kind of look at the fragmentation pattern if you're not sure, and you know that it's been labeled because you can look for the characteristic fragments that you have. So.